We've been making really good use of this theorem. Let's continue to make good use of this theorem. I'm going to hit once again this thing here. The gradient is normal, orthogonal to level curves, or also I can kick this up, we're working in more dimensions, level surfaces. So here's the example I want to look at in this video here. Find equation of the tangent plane to x squared y plus yz squared is equal to 5 at the point 1, 1, 2. So this equation, this defines a surface. And the thing is that like this is a really, this would be very, very difficult to plot this surface. It's some weird, I don't know what it looks like. I'm just going to draw some pictures here, and I'm not sure exactly what it looks like here, but it's the set of all points that when you plug them into this equation, you get 5. So, and we plug in, let's just check this every so often I botch this up. X is 1, 1 squared times y is 1. 1 squared times 1 is 1 plus 1 times 2 squared. 1 plus 4 does give us 5. That checks out. But the thing is that, okay, so maybe like this 1, 1, 2 here is right there. There's going to be some kind of tangent plane at that point here. We want to find the equation of the tangent plane at that point. Okay, so let's think about this in the context of what we've been doing here. Well, what do we know about the gradient? The gradient is normal to the surface. And if you're normal, if you're orthogonal to the surface, you're also orthogonal. You're also normal to the tangent plane. So there is some normal vector coming out here. It's normal. It's orthogonal to the surface. We know that from properties of the gradient here. Level curves, I should say level surfaces. Why is that? Maybe I should emphasize, why do we have level curves? Why do we have level surfaces going on here? Our function f of x, y, z is x squared y plus yz squared. The level curves, the level surfaces are when this is equal to some constant here. Here we're setting it equal to the constant 5. That gives us level surfaces. This is equation of our tangent plane. This is how we're going to go about doing it. So how do we attack this? The gradient evaluated at the point, the gradient of the function, f of x, y, z, evaluated at the point 1, 1, 2. This will give us a normal vector to our surface and thus to our tangent plane. And what do we need for an equation of a plane? A point, 1, 1, 2, and a normal vector. Okay, so without further ado, let's go ahead and do the corresponding calculations here. So the gradient of f will be, okay, so the x partial derivative is going to be 2xy. The y partial derivative is going to be x squared plus z squared. And the z partial derivative will be 2yz. We want the gradient evaluated at the point in question, 1, 1, 2. So plopping this in gives us 2 times 1 times 1 is 2. 1 squared plus 2 squared is 5. 2 times 1 times 2 is 4. So this is going to be the normal vector for our plane. And our point is 1, 1, 2. So now it's a very easy application. It's a very easy application of section 12.5 stuff to write down the equation of the tangent plane. So it's the first coordinate of our normal vector is 2 times x minus the x coordinate from our point 1, plus the second coordinate of our normal vector is 5 times y minus the second entry of our point 1, plus 4 times z minus 2, and all of that equal to 0. So yeah, once again we see this feels like a very, very difficult problem here. And once again, just like in some of the previous problems that we've seen, the word gradient doesn't appear in this problem, but the gradient is the key to answering this. And just knowing all of these properties here is very, very useful for working with the gradient, and answering lots of problems from this section here. Okay, so that is how we find tangent planes using the gradient. To finish off this video, maybe this should have gone in the previous video, but here's a second pre-class problem for the section. Find the maximum rate of change of this function, f of xy is x squared plus y cubed, at the point 2, 1, along with a unit vector in the direction in which that maximum rate of change occurs. When I say maximum rate of change, I'm looking for the maximum rate of increase there.